Welcome back everyone. In this lecture we will review what we have done so far and then we will move to the representation theory of finite groups. So, let us begin. So, let A be an associative algebra as before. Over C. So, let me actually quickly recall some of the terminologies that actually we introduced about representations of capital A. So, recall that representation is just an algebra homomorphism from A to endomorphism of V, where V is just a vector space over C. So, this is an algebra homomorphism. So, this is what we call it as representation, and this V is called a representation space or a representation. So, this is a representation space or just a representation, and we also actually call the degree of the representation to be the dimension of V. So, the degree of the representation is just the dimension of V over C. So, let me just quickly go through some of the terminologies that we introduced. So, we defined what is called subrepresentation. So, they are just subspaces of V which are invariant under the action of each element of capital A. So, now what is irreducible? So, and representation so V is said to be irreducible if 0 space and the entire space are the only subrepresentations of V. So, now once we have irreducibility, we can define what the notion of complete reducibility. So, completely reducible. A representation is said to be completely reducible if it is isomorphic to direct sum of irreducible representations. A representation V is called completely reducible or sometimes we use the other terminology called semi-simple if V is isomorphic to direct sum of finitely many irreducible representations. So, as I said before, in this course we will be only focusing on the finite dimensional representations. So, that already forces that the number of components here in this direct sum that must be finite. Anyway, so this actually kind of completely reducibility actually says that so this given representation can be decomposed into finite direct sum of irreducible representations. So, for some reason if we know that given representation is completely reducible, then we can actually focus on what are all the irreducible subrepresentation it has and then how to decompose that given representation into direct sum of these irreducible subrepresentations. So, we will actually show that in this course the category of finite dimensional representations of finite group must be actually semi-simple. That means each finite dimensional representation of finite group must be completely reducible. So, this is something I will prove later. Okay, so let me just make some noise about this irreducibility. So, you can easily prove that any finite dimensional representation must contain an irreducible subrepresentation. So, let me make a few statements which are true in any general category of representations over any algebras. So, these statements like you can actually state it for state it in the any settings. Okay. So, the very first statement is that irreducibility will imply indecomposability. So, that is something easy to prove. So, irreducible representations must be indecomposable representations. So, irreducible implies indecomposable. So, it is basically one line proof. So, if we start with a representation that is irreducible. So, let us say V is given irreducible representation of let us say capital A. So, then it cannot be indecomposable, because if it is it cannot be decomposable. If it is actually decomposable, so then V must be isomorphic to direct sum of V1 and V2, where both Vi will be non-zero representations. So, suppose V is decomposable, so then we have this for sure. So, now one can easily prove that in this case that V must contain non-trivial subrepresentation. Suppose pi is the given isomorphism from V to V1 direct sum V2. So, if this is an isomorphism of representation that is given, then we can actually simply take pi inverse of V1, and then we can easily see that this must be a non-zero proper subrepresentation of V. So, this is a non-zero proper subrepresentation of V. So, that means V cannot be irreducible. So, that would imply that V is not irreducible or V is reducible. So, that implies that irreducibility should imply indecomposability. So, now if we take any finite dimensional representation, then we can prove that it must contain irreducible subrepresentation. So, in a way irreducible representation play an important role in building given representation. So, I will actually discuss about that in a minute. So, maybe we will actually prove this statement that I have made. So, if we start with finite dimensional representation, any finite dimensional representation of A. So, this contains an irreducible subrepresentation. So, let us start with V, which is finite dimensional representation of A. Suppose V itself is irreducible, then there is nothing to prove, because it contains itself as subrepresentation. So, we can assume that V is not irreducible. So, then what we can do, we can actually look at all possible subrepresentations of V which are proper and non-zero inside V. So, look at this collection. So, where W, which is a subrepresentation of V, and this W is non-zero, and it actually contains, so it is proper inside capital V. Okay. So, maybe like to make it this argument to work for even any representation, we can assume that this W is just a subspace of V, non-zero subspace. So, if V is 0, then actually there is nothing to prove, but V is non-zero. So, assume that V is actually non-zero, then consider this collection. So, let us call it script A. So, now what we can do, we can actually look at all possible dimensions of W, and then we can choose minimum dimensions among these dimensions of W. So, choose W in script A such that since the dimension of W is the minimum possible. So, if we choose a sub-representation that has minimum possible dimension, then it is immediate that that must be irreducible. So, because so claim is W is irreducible, because if it has some proper non-zero sub-representation, let us call it U. If this is proper non-zero sub-representation of W, so then that would imply that dimension of U is strictly less than dimension of W. So, that actually leads to a contradiction because U is an element of script A again. So, these two properties will actually give us contradiction. So, that would imply that so we have this W irreducible inside capital V. So, that means given any 5-dimensional representation, we can always choose an irreducible sub-representation inside that. So, indeed one can strengthen this property little bit stronger if we are working with 5-dimensional representations. So, what one can prove? One can prove that we can have a filtration of sub-representations whose successive quotients actually are nothing but irreducibles. So, let us prove this stronger statement. So, here is a proportion. So, this is somewhat very strong proportion than earlier. So, let us first define what is a filtration. So, a filtration of V is a subsequence is a sequence of sub-representations. So, one contained in another. So, let us write it here, a filtration. So, this is a filtration of V. It is a sequence of sub-representations. So, they satisfies the following. So, you take 0 which is the start of the filtration V0, which is contained in V1, contained in V2 and so on. At the end you will have the full space. So, let us call it that is Vk. And this sequence of sub-representation, one is contained in another and reaches from the 0 space to all the way full space, that is called filtration. So, our proportion actually guarantees that if we are working with the 5-dimensional representations, then there is always a filtration that we can find such that the successive quotients Vi modulo Vi minus 1, they are irreducible. So, let us start with V being 5-dimensional representation of A, and we can immediately prove that. So, then there exists a filtration. So, let us call it V0, which is starting point V that is the 0 space, which is contained in V1 etc., which is contained in Vk, which is the full space, such that so this filtration satisfies the property that the successive quotients, so which is Vi modulo Vi minus 1, they are the quotient representation, they are irreducible. So, we have this filtration satisfying this property. So, let us prove this. This is indeed very important result that actually tells us that any 5-dimensional representations, they are indeed built by these irreducibles. So, let me make some comment about it later. So, let us first prove this. So, the proof actually uses just an induction on the dimension of V. So, we use induction on the dimension of V. Of course, the base case that is very clear. So, base case either you can take it to be 0 dimensional space or 1 dimensional space, or dimension V being irreducible, the space V being irreducible. So, that we can take it as a base case. So, which includes both 0 and 1 dimensional. So, the base case which is V is irreducible, and this is clear, because if V is irreducible, we can just take this filtration which contains V naught as 0 and V 1 as just capital V. In that case, V is irreducible. So, otherwise what would happen? So, we can actually if V is not irreducible, so then there exists non-zero proper subspace subrepresentation. So, you have this non-zero proper subrepresentation of V. So, you have subrepresentation of capital V. So, now using this, what we can do, we can actually look at this new representation which is the quotient, which is V modulo V 1. So, now it is clear that the dimension of U, which is exactly dimension V minus dimension of V 1, which is strictly less than the dimension of V. So, because the dimension is smaller than dimension of V, we can use induction. So, we can use induction and get a filtration for U satisfying the required property. So, we get a filtration of U. So, let us call it U naught, which is contained in U 1, contained in etc., contained in U k minus 1, which is the full space U, which is V modulo V 1. So, where again we have the same required property. If you take U I modulo U I minus 1, so then that must be irreducible. So, these are irreducible. So, this is guaranteed by induction. So, now what we can do, we can actually use the quotient map and then pull back all these representations and then get filtration of capital V. So, what we do now, so let's name this quotient map to be pi from V to V modulo V 1. So, we know that this quotient map is supposed to be homomorphism between the representations. So, this is the quotient map. So, now once we have this quotient map, what we can do, we can actually pull back all of these subrepresentation that appear here in this filtration of capital U. So, then that is going to give us filtration for capital V. So, we just simply take for example, pi inverse of 0. So, that is going to be V 1, and V 1 is already contained in V 0, and then we can simply take pi inverse of U 1. So, that we will call it V 2, and then that is contained in etc., contained in pi inverse of U k minus 1. So, that is exactly V modulo that is exactly capital V. So, by setting this, so basically we set V I equal to this pi inverse of U I minus 1 for I equal to 1 to k minus 1, V I plus 1, yeah, we can simply take Vi plus 1 here. So, Vi plus 1 you take it to be pi inverse of Ui for I ranging from 0, 1 etc. up to k minus 1. So, then it is clear that we have the following filtration. Vi plus 1 we take it to be pi inverse of Ui for I ranging from 0, 1 etc. up to k minus 1. Then it is clear that V naught is 0, which is contained in V1, contained in V2 etc. contained in Vk. So, we get a filtration. So, filtration of capital V. But now using the first isomorphism theorem, one can see that U I modulo U I minus 1 is going to be isomorphic to. So, you have a map pi which actually a quotient map from V to V modulo V1. So, if you look at the U I here, the inverse image is nothing but V I plus 1. So, that means this U I modulo U I inverse is going to be exactly isomorphic to V I plus 1 modulo this V I. So, let us restrict the map this pi restricted to V I plus 1. So, this is going to define a map from V I plus 1 to U I. So, this is because by definition of V I plus 1. So, you can see that by definition of V I plus 1, this is nothing but the inverse image of U I. So, when we actually restrict our pi to Vi plus 1, then we are going to get a map from the pre-image to the image. So, now if we actually just look at the end, because since V1 is contained in Vi plus 1, okay. So, we are interested in actually, okay, let's actually compose the maps and then see what happens. So, we have pi restricted to Vi plus 1, which gives a map from Vi plus 1 to Ui, and then you have the quotient map from Ui to Ui modulo Ui minus 1. So, this is the quotient that we are interested in understanding. So, this is the quotient that we are interested in understanding, and we are claiming that. So, this quotient is exactly isomorphic to Vi plus 1 modulo Vi. So, this is the claim that we are making. So, now if you work out this composition, so look at this composition. So, then we can easily see that. So, let us call that map maybe pi dash. So, this is the map we are talking about. So, this is the map which is composition, this is the pi dash. So, then you can see that pi dash defines an onto map from Vi plus 1 to Ui modulo Ui minus 1. This is onto homomorphism. So, let us look at the kernel of this map. So, the kernel of pi dash. So, once we determine the kernel, we know that Vi plus 1 modulo the kernel pi dash using the first isomorphism theorem. So, it will be isomorphic to Ui modulo Ui minus 1. So, if we prove the kernel is exactly Vi, then we are done. So, what will be the kernel? So, the kernel is going to be those vector in Vi plus 1 that is indeed mapped by pi dash to 0. So, that is indeed 0 inside Ui modulo Ui minus 1. Since pi dash is just a composition of pi with this another quotient map. So, you can see that if you take V here, then that is mapped to pi of V, and that pi of V being mapped to 0, that means using pi dash. So, that means pi of V must lie inside ui minus 1. So, the kernel of this second map is nothing but ui minus 1. So, because of that, you can easily see that pi dash V is 0 if one implies pi of V is inside the ui minus 1. So, that implies that V is inside pi inverse of ui minus 1, which is exactly Vi. For the converse, if we take V from Vi, so then that would imply immediately that pi of V is in the image, which is ui minus 1, and that would imply immediately that pi dash of V must be 0. So, by just tracing the maps, you can easily see that the kernel of pi dash is nothing but Vi. So, that proves the claim that we were interested in. So, Vi plus 1 modulo Vi is indeed isomorphic to ui modulo ui minus 1. So, if you go back to the filtration, then you can see that the filtration actually starts with V naught and ends with Vk, and we already know that this V1, that representation, so that is indeed, we can choose it to be irreducible representation. So, all these arguments actually work without V1 being irreducible, but now because we are interested in filtration that actually satisfies the property that successive quotients must be irreducible. So, that means we need to choose V1 to be irreducible. So, which is guaranteed from our earlier result. So, we choose V1, that is irreducible subrepresentation of V. So, once we make sure it is irreducible subrepresentation, then it is clear that the filtration that we have actually have, which satisfy the property that successive quotients are actually irreducible. Okay, so this actually completes the proof that I wanted to do. So, basically it says that if we take any 5-dimensional representation, then we can always have a filtration such that the successive quotients are irreducible. Actually, what does it say about the representation? So, basically it says that any 5-dimensional representation can be built using irreducible representations. So, maybe I will explain this more in my next lecture. So, I will stop here. So, we will actually see how these irreducible blocks indeed we put them together to get any 5-dimensional representation in the next class. Thank you.